Welcome back. In this video, we'll be talking about the average rate of change of a function, and we'll also be talking about the behavior of the graphs of our functions, increasing, decreasing, maxes, mins, and all those sorts of things. But first, to start with the average rate of change of a function, this is going to tell us how much does the function value change, how much does the y value increase or decrease over some interval of x values. That's the thing here. We're looking at as x changes from one value to another, how does the value of y change? And the example that I have here is a function that gives us, the f of x tells us the population of a town on year x. So when we say that in the year 2000 that there's 550 people, we're really saying that f of 2000 is 550. And in the year 2010, the population is 750 people. That means that for our function, f of 2010 is 750. Now, if you're interested in how is this population changing over this 10-year period, if it was originally 550 people and then it ended up with 750 people, then that means that over that 10-year period, you had an increase of 200 people. And an increase of 200 people over 10 years is the same thing as an increase of 20 people per year. That's not to say that we're having exactly 20 people coming to the town every year. All we know is that somehow over that 10-year period, the population increased by 200 people. So if you had 200 people in total over 10 years, then that averages out to 200 divided by 10, or 20 people per year. Now, as far as what does this do for our graph of this function, if you're really thinking about this measurement that I have here of people per years, people is a measurement of the y value for our function. So in other words, this is how the y value is changed. And years, those were the values for x. In other words, we're doing essentially finding a slope yet again. When we're looking for this average rate of change in people per year, we're looking for how does the y value change as the x value changes. So really, when we're looking for the average rate of change from 2010 to from 2000 to 2010, all we're really doing is looking at the slope, connecting the points on our graph where x is 2000 and x is 2010. So the moral of the story here is if we're looking for an average rate of change, essentially all we're doing is looking for a slope. And that's what I have here formally defined, that the average rate of change for a function over some interval going from a to b, and of course, for this to actually be an interval of numbers and not just a single number, then the endpoints can't be the same. It can't be going from 2 to 2. It has to be going from one number to another. And the average rate of change is just finding the slope of the points that pass through when x is a and when x is b. So if we're thinking about this little picture that I have here, I've got a picture of my little function, my parabola that I've got drawn in black here. That's my function f. And I have a point here when x is a, and I have a point here where x is b. So if we wanted to know how does the parabola change as we go from a to b, we're finding the slope of the line that connects these 2 points. We're finding the slope of the line that connects a f of a with b f of b. And we can see that if you had those 2 points, then the change in the x values and the change in the y values would be exactly what we have here. The y value minus the y value, f of b minus f of a for the numerator, and b minus a, the x value minus the x value for the denominator. The name that we give to this line, the line that crosses through our function when x is b and when x is a, we call that a secant line. Secant from the Latin meaning to cut or to slice. So here, whenever we're looking at a secant line and finding the slope of it, we are finding the average rate of change of a function. So We could phrase it as we are finding the average rate of change of f of x. We could also phrase it as we're finding the slope of the secant line that cuts through f of x in these 2 points when x is a and x is b. But both of those are exactly the same thing. That if you're finding the average rate of a function f, average rate of change, you are also finding the slope of that secant line that passes through that function f. So let's get into this. We're looking for the average rate of change of this function f, which is 3x squared x squared minus 3x plus 2. And we want to do this over the interval from 1 to 3. And so first thing that I'll do before I do anything else is find out what is f of 1 and what is f of 3. So f of 1, that would be 1 squared minus 3 times 1 plus 2, which is 0. So in other words, we have the point 1, 0 on our graph. And I'll do the same thing for f of 3. f of 3 would be 3 squared minus 3 times 3 plus 2, which when I run that through my calculator, I get the value of 2. So that means that the second point that's on our graph is the point 3, 2. So we know 1, 0 is the point on our graph, 3, 2 is the point on our graph. So for this average rate of change from 1 to 3, that would be the slope. And the slope we find, just like we always do, the change in the y values minus the change in the x values. So the change in the y values, 2 minus 0. And the change in the x values, 3 minus 1. So we have an average rate of change of f over this interval of 1. In other words, as we go from 1 to 3, every time we increase x by 1 unit, we also increase y by 1 unit on average. Or in other words, since we're increasing the x value by 2 units and the slope of this secant line that we have that slices through those 2 points has a slope of 1, that means that the y values also increase by 2 as well. So lots of different ways that we can interpret this. So our average rate of change for this function being 1 over this interval tells us that the x and y values on average are changing by the same amount. The fact that this is an average rate of change is positive tells me that the graph of this function is one that's going upwards between 1 and 3. So that's another little consequence that we can get out of it. Just like any other thing that has a slope involved, negative slopes are telling you things that are heading downward. Positive slopes are telling you things that are trending upward. So if we're thinking about this slope that we're looking at here being positive 1, that tells us that over this interval, this function must be going up, must be increasing in some way. Now, for the next part, finding the equation of the secant line, which crosses when x is 1 and x is 3, well, we actually have everything we need because we know for this secant line that the slope would be the same as that average rate of change, which we've already found, 1. We already know 2 points on the secant line. It's the same 2 points that were the 2 points that we used for the average rate of change. So points that are on the line happen to be 1, 0, and 3, 2. So we actually have everything we need. We can just create the equation of our line using slope point form. Y minus y1 equals slope times x minus x1. And I'm going to use this point. I'll use the point 1, 0. You, of course, can use either of the 2 points, and it should turn out to be the same. But I'll use 1, 0. So putting in 0 for y, putting in 1 for my slope, and 1 for x. And then just simplifying, I have the equation of my line, y equals x minus 1. So this y equals x minus 1, that should be the equation of the secant line that should pass through this function, f of x equals x squared minus 3x plus 2, at these 2 points. It should pass through when x is 1 and should also pass through when x is 3. Now this is to sort of tie this back to 3.1. I've taken the same drawing that I had of a secant line, and I've just rewritten it in a slightly different way here. Instead of going from point A to point B, I've instead written it out as we're starting at point x, whatever the value of x is, and instead of saying, well, this will be some different value, I'm instead saying how far away the 2 points are from each other. So I'm saying that the first point is at x, and that the next point is at h units away from the first point. So in other words, the second x coordinate is x plus h. And so if x is the x value, then f of x is the y value, because that's how it works when we evaluate a function. Whatever the x value is, put it into the function, and that tells you the y value. So similarly here, if the input value is x plus h, then the output value for our function should be f of x plus h. Just like how when we said it was the points A and B, that this was A with f of A and B with f of B. Same idea here, just we're writing it in a slightly different way. And the reason we're doing this is to show the connection between this secant line and the difference quotient that we had from back in 3.1. If you were to find the slope of this secant line, you would be taking the change in the y values, f of x plus h minus f of x, that would be that, divided by the change in the x values, x plus h minus x, which is that, which of course, that just simplifies down to give you just h. So lo and behold, as it turns out, for this secant line that we're looking to construct, the slope of that secant line actually is the difference quotient that we found back in 3.1. So if you wanted to really make the connection here, the idea is that the difference quotient tells you the average rate of change. And that also is the same thing as telling you the slope of a secant line. That all three things are really interchangeable. If you have a function f of x and you find the difference quotient, that's something that is also could be used to calculate an average rate of change, and that also is the slope of a secant line. So all of these things are really just interchangeable with each other. So if you now want to go back to 3.1, when we were finding those difference quotients, what we were really doing was finding an expression for the average rate of change in terms of x, the initial x value, and h, the distance to the second x value, because that's what we have here. That's exactly what the x and the h represent. X is where we start, and h is how far we have to go to get to that second point. Now, for some of the definitions that we're going to work with the next little part here, I'm going to be talking about intervals that are open. And so when I say an open interval, I'm talking about intervals that don't contain their endpoints. So things like the interval from 1 to 5, that would be an open interval because the 1 and the 5 are not included. Similarly, if I were to say the interval from negative infinity to 2, not including the 2, that would be another example of an open interval. A closed interval would be something like 3, 5, including the 3, including the 5. I'm including my endpoints, so this would be one that's not an open interval. It's a closed interval. So here when I'm talking about an interval I, I'm talking about an open interval. So these are intervals that are not containing their endpoints, so round brackets only. And if we want to describe increasing functions, decreasing functions, and constant functions, it's fairly natural what it means. It's a little bit different the way I have to put it in words to make it mathematically precise. But if we want to describe an increasing function, we'll say that if our function is increasing on an interval, then whenever you have a smaller x value and a larger x value, the smaller x value has a lower y value for that function than the larger x value does. Or in other words, if you've got an interval where you're increasing and you pick an x value and a second x value, a smaller one and a larger one, that f of the first x value has to be less than f of the next x value. That's how you know when a function is increasing or heading upwards. And opposite would be true if you're looking at a decreasing function. If you're looking at a decreasing function, the y value for the first point should be greater than the y value for the second point. That would be something that's decreasing. And then, of course, the third option would be if they both have the same y values, then we're talking really about a function that is constant, that it's just a horizontal part. So this is true for any x's in that interval. So if you have something, for example, where it's decreasing, then pick any two x values you'd like, and the y value for the first point and the y value for the second point should decrease from each other, that the first point should have a larger y value than the second. Or if you're thinking about things that are constant, so in this little interval where things are constant, picking any 2 points you'd like, the first x value and the second x value, they both have the same y values for that little segment of the graph. So this is a fairly natural idea. When a graph is going up, it's increasing. When it's going down, it's decreasing. And if it's horizontal, then it's constant. And similar ideas here, we can introduce the idea of local maxes and local mins, or relative maxes or relative mins. These are the same thing. When I say that something is local or relative, those both mean exactly the same thing. Here, when we're talking about a local maximum or a relative maximum, we're talking about a point where the y value is larger than all the other points that are nearby it, in an interval around it. So for example, if I were to just give you a little squiggle here of a graph, pretend this is my graph for a moment. There we go. This point here, we might say that this point would be a local maximum, because at that point here, the y value for the point is larger than any other y value immediately around it, in its little neighborhood around it. Similarly, this would also be a local maximum or a relative maximum. It's larger than anybody else around it. This would be a local minimum or a relative minimum. This would be smaller than anyone else around it. Other little bits of terminology here, just in general, relative maxes, relative mins, we would call them relative extrema or local extrema. Those are the local maxes and mins. And just one little bit of language use here. So for words like minimum, maximum, and extremum, those Latin words, the plural of them would be minima, maxima, and extrema. So when you hear me say minima, I'm actually referring to the plural of minimum. So more than one local minimum would be local minima. And more than one local maximum, they would be local maxima. More than one extremum, that would be extrema. So we've got ourselves a little graph. I've got a couple of points that are plotted here. We can see for this graph that it's the graph of x cubed minus 3x plus 2. I've got the point 1, 0. That's my x-intercept, or one of the x-intercepts. I've got the point negative 1, 4 also on the graph. And the questions that we have for part A, where is this function increasing? Over which intervals? And so just looking at our graph, where is it increasing? Well, if we're looking from left to right, where are we going up? We're increasing until x value reaches negative 1, and then we'll increase after 1 as well. So there looks like two intervals where this graph is increasing. So you could say that it's increasing from the far left up to negative 1. Not including the negative 1, because remember, for increasing or decreasing, we're using open intervals. And also it's increasing from 1 and onwards. And similarly, where is it decreasing? It's decreasing just in this little chunk here between -1 and 1. So the interval from -1 to 1. While I'm here, this is sort of a good point to mention why we're talking about intervals that are open for increasing versus decreasing. If you're thinking about this point that we have here where x is -1, that's not a point where you're increasing or decreasing. That's where you're changing from you were increasing up to that point and you're decreasing after. This point is actually you're not increasing or decreasing. This is a point where you're changing direction. In fact, that's a point that's a relative maximum. So where does it have a relative maximum? Well, at x equals -1. That's where the maximum happens. What is the maximum value for the function? The maximum value is the y value, and the y value happens to be 4. That's one thing just to be careful here, that when we're talking about minima and maxima and all the rest, there's two different things that I could be interested in. I could be interested in where does the maximum or minimum happen? That's the x value. Or I could be interested in what is the minimum or maximum value? That's the y value. So where does the maximum happen? It happens at -1 for x. What is the maximum value? That's the y value, which is 4. And let's do E and F. Where does it have a local minimum? So here we decreased, then we increased. The local minimum happens when x is +1. And what is that minimum value? That minimum value is y value of 0. Now, just to be careful here, that when we're talking the local minimum and local maximum, these are the values that are smallest in their little neighborhood or largest in their little neighborhood. That's not to say that they're the smallest value overall. In fact, if you're looking at this graph goes in both directions forever. It increases forever in this direction, and it goes down forever in that direction. As it turns out, for this function, there would be no largest value and no smallest value. So when we say that the minimum value is 0, it's a local minimum value. That's the smallest in its nearby vicinity. And for the maximum value, that's the largest value in its nearby little vicinity. But we could also introduce the idea of absolute extrema as well, not just the local minima and maxima. What would be the absolute minima and maxima? What would be the largest and smallest values overall out of all the values of our function? And so that's what we're going to introduce here for absolute maxes and absolute mins. An absolute maximum is one that has the largest y value for all the x's in the domain. So in other words, it is the largest y value out there. That would be the absolute maximum. And similarly, the absolute minimum would be smaller than all the other y values for every other y value in the domain. Now, of course, one thing that's true is if you're an absolute maximum or an absolute minimum, you would also be local as well. If you're the largest y value out of all the y values, then you're also larger than everyone around you. So if you are the absolute maximum, you would also be a local maximum. Similarly, if you're the smallest y value of all, then you're also smaller than any y values that are near you. In other words, if you are an absolute minimum, you must also be a local minimum as well. And I'm mentioning that because for this example here, we're looking at the values of our extrema in this function that I've got below. It's a very zigzaggy little function. And there's 3 points in particular that I'm going to want to talk about. The obvious ones here, 3, 4, 5, 2, and 1, -2. I'm going to talk about them. I just have to remind myself that when I'm classifying my points, A point might be a relative minimum, but it might also be a local, an absolute minimum as well. And similarly, a point might be an absolute maximum, but that would also mean it's a relative maximum as well. So we'll need to think about all of the above. So let's first start with our relative extrema. So let's look for relative maxes. And if we're thinking about a relative max, the only relative maximum that I can see is the one that we have here. That would be the only point where the y value is larger than any other y values in its nearby vicinity. So relative maximum at x is equal to 3, and the value is 4. And if we're thinking about relative minima, same sort of thing could be said for those ones as well, which is that for relative minima, you have 2 points in particular. We have the point 5, 2 and the point 1, negative 2. And for both of those, these are both smaller than anybody else in their nearby vicinities. So we have 2 relative minima. So one of them at x being 1, and for that one the value is negative 2. And the other one happens to be when x is 5, and the value for that is positive 2. So that would be the relative max and the relative min. Now let's think about absolute maxes and absolute mins. I'm going to say that there's no absolute maximum for this one. And the reason why there's no absolute maximum, if we're looking at this function, it continues to increase forever in that direction, and it also goes up forever in this direction. There will be no largest y value on the graph of this function. So there is no absolute maximum going to be there and to be found. But we do have an absolute minimum. So if we're looking at this point that we had here at the bottom, 1, negative 2, that has not just the smallest y value in its little nearby neighborhood, but it also has the smallest y value out of all the points that are on the graph. So if we were to say what is the absolute maximum, if we were to say what is the absolute minimum, we could say that we have an absolute minimum when x is equal to 1, and the absolute minimum value is negative 2. So this point, 1, negative 2, it's both a relative minimum and it's also an absolute minimum. So when x is 1, the absolute minimum value is negative 2, and that's also a relative minimum value.